Hello, everybody. I hope that you are fine, safe and sound. In this video, we are going to talk about method of variation of parameters. So this is again about finding a particular solution for a non-homogeneous equation. So we have non-homogeneous linear differential equation with constant coefficients, non-homogeneous. So we have a function on the right side of the equation, constant coefficients. So AI's are constants. We use a method of undetermined coefficients. When the function b of t has a polynomial annihilator. We did this in lecture 15, the method of undetermined coefficients. But in order to use this method, the function bt must have a polynomial annihilator, meaning the function bt has to be of a certain form, a linear combination of functions of the form polynomials, exponential, sine, cosine. Product and linear combination of the products. But there are some very simple functions which do not fall into this category. But some simple functions like 1 over t or square root of t or secant t, derivatives of these functions, all the derivatives are independent. So we cannot find polynomial annihilators for these functions. So functions like these do not have polynomial annihilators. So if your function bt on the right side of your equation is a function like this, 1 over t, root t, or secant t, then the method of undetermined coefficients doesn't work. So in this case, when the function b of t does not have annihilator, we cannot use method of undetermined coefficients. What do we do then? If you remember back to systems, when we were considering non-homogeneous systems, we used the method of variation of parameters. So in this case, we use the method of variation of parameters. Okay, so to explain how to use this method, we need to convert our equation into a system first. We convert the equation into a system. So system non-homogeneous, dx dt equals matrix A times x plus vector B. Now, how do we do this? Recall. How do we convert the equation into a system? Our variables, x1, x2, xn, remember, x1 is the unknown function y, and x2 is derivative of y, x3 is the second derivative, and so on, and the last one, xn, is n minus first derivative of y. And in this case, the matrix A turns out to be 0, 1, and then zeros, 0, 0, 1, zeros, 0, 0, the last one is 1. And in the last row, we have the coefficients, but we take them to the other side, and we start from an minus an minus 1 minus a1. And for B, we have all the equations are 0 except the last one. In the last one, we have the function B from the equation. So we convert the given equation into a system in this way. Remember, we did this in the beginning, I don't remember the lecture number, when we were first discussing linear equations of higher order. All right, now, so we have this system. We have this system with this matrix A and this vector B. Now let's remember the variation of parameters for systems. Recall variation of parameters for systems. So first, we write, first we find a fundamental matrix. First, find a fundamental matrix. C of the homogeneous equation homogeneous system dx dt equals ax. Then write solution x as the fundamental matrix times a column matrix of functions v of t. V of t, in general, when you write the solution of the homogeneous system, you take your fundamental matrix and you multiply it with constants. So C1, C2, Cn, constants of this vector, but for variation of parameters, instead of functions, instead of constants, we take functions, v1 of t, v2 of t, vn of t. So the question is to find this vector v. Find v so that x equals the fundamental matrix times v is the solution of the non-homogeneous system dx dt equals ax plus b. Okay. All right. So we take this form and plug it in to plug it into our system. So if X is the matrix C times V, then its derivative by the product rule, derivative of this matrix C with respect to T times V plus this matrix times V. But since phi is a fundamental matrix of the homogeneous system, derivative of C is the matrix A times the matrix C. And we regroup the terms. The order of multiplication is not important. And the matrix PC times V is what we called X. And we want this to be equal to AX plus B. So by comparing the two sides, we already have A sub X. So we need PC times V equal to B. I'm sorry, not V. This should be derivative of V. I forgot to differentiate. The matrix PC, being a fundamental matrix, has an inverse. So if we multiply both sides with its inverse, we get derivative of V equal to inverse. I'm sorry, my writing is not very good. Okay, inverse times B. So this is the derivative of the vector function V. To find V, we just integrate this with respect to T. And in this integration, if you keep the integrating constants, then this X and substitute this V back here. Oops, I'm sorry. Back here. So this gives you the general solution. If you keep the integrating constants, this X gives you the general solution. Okay, now let's look at our case. Okay, in our case, the fundamental matrix has a special form. Remember, in our case, the system comes from a differential equation, nth order differential equation. So it has n independent solutions, the homogeneous equation. Then for the system, remember for the system, x1 is y, x2 is y prime, x3 is y double prime, and so on. And xn is y to the power n minus first derivative of y. So in the fundamental matrix, remember in the fundamental matrix, each column is a solution of the system, but to be a solution of the system, the variables x1, x2, x3 should be in this form. So if your first entry of the column is y1, then the other entries are the derivatives up to the n minus first derivative. So this is what is y1, y2, yn are independent solutions of the corresponding homogeneous equation. equal to 0. So this is our fundamental matrix. Okay. Solution of the non-homogeneous, the original equation, is the first component remember, our unknown function y is the first component of the vector solution of the system. So is the first component of the solution x, which is the fundamental matrix times v, where v is the integral of inverse of the fundamental matrix times the vector b, and the vector b is the vector 0, 0, the last entry is b. So basically, for nth order linear non-homogeneous differential equation, we first find the independent solutions, y1, y2 up to yn, of the corresponding homogeneous equation, form the fundamental matrix. From these solutions, form the fundamental matrix using this vector b and the fundamental matrix, find the vector v, and use this v here to find the solution x, and our solution is just the first component of the solution. Well, I guess it sounds complicated, so let's work out an example. I'm hoping that in the example it will be more clear. So, example, let's solve the equation 4y double prime plus y equals 2 secant t over 2. Note that we cannot solve this using the method of undetermined coefficients because the secant t over 2 does not have an annihilator. Okay, so the first thing is to write it in the standard form. So we need to divide by this coefficient 4 because remember, we always start with the highest derivative of y alone. So divide by 4, we have 1 over 4 y equals 1/2 secant t over 2. So we first write the corresponding homogeneous equation, y double prime plus 1 over 4y equal to 0. And from here, we write the characteristic equation, lambda squared plus 1 over 4 equal to 0. So lambda squared equals minus 1 over 4. Lambda is plus or minus 1/2 I. We have complex roots, plus minus 1/2 I. So the solutions, the first solution is cosine t over 2, because in our complex solution, complex root, the number b, imaginary part, is 1/2. The number a, real part, is 0. And y2 is sine t over 2. Okay. Now, using these solutions, we form the fundamental matrix. So in the first row, we take the solutions, cosine t over 2, sine t over 2. And in the next row, we take the derivatives. So minus 1/2 sine t over 2 and 1/2 cosine t over 2. And then we need to find the inverse of this matrix. To find its inverse, First, we need its determinant. Its determinant, if you multiply the main diagonal, 1/2 cosine squared t over 2 minus, you multiply the other diagonal, minus 1/2 sine squared t over 2. So this sum is just 1/2. So for a 2 by 2 matrix, how do we find the inverse? We take 1 over the determinant, and in the matrix, we interchange the elements of the main diagonal. And we multiply the other the elements in the other diagonal with minus 1. So we have the matrix dividing by 1/2, meaning multiplied by 2. So cosine t over 2 minus 2 sine t over 2, sine t over 2, 2 cosine t over 2. So this is the inverse matrix. And our vector B, the first entry is 0, second entry, we have a 2 by 2 system. The function on the right side of the given equation, what was it? Let's 1/2 secant t over 2. And then we multiply it. We multiply the inverse of our fundamental matrix with this vector. So let me write the inverse matrix. Okay, so the first entry, cosine times 0 is 0, minus 2, but there's a 1/2 here, so minus sine t over 2, secant t over 2. And the second one, sine t over 2 times 0 is 0, 2 times 1/2 is 1, cosine t over 2, secant t over 2. Remember that secant is 1 over cosine. So the second entry is just 1. All right, now we need to find the integral. Remember, V is the integral of this vector. So we need to find the integral separately. For the integral of minus sine t over 2, secant t over 2, remember secant is 1 over cosine. Derivative of cosine is minus sine, but we also get the derivative of inside t over 2 is 1/2. So the ni derivative then 2 times natural logarithm of absolute value of cosine. I'm sorry, let me go back to the beginning. Okay, the original equation, on the right side we have the secant function, but secant function is not continuous everywhere. So I need to give an interval for t. I need to give an interval for t where secant t over 2 is continuous. Remember, secant is not continuous when cosine is 0. Of course, you can consider different intervals, but in any case, in order to be complete, the question has to be given together with an interval for t, because the secant function is not continuous everywhere. So I give the interval as from minus pi to pi. So for t over 2, at the endpoints, minus pi and pi, t over 2 is minus pi over 2, pi over 2. Between minus pi over 2 and pi over 2, cosine is not 0, it's positive. So secant t over 2 is continuous. So in general, for the ni derivative, I take cosine absolute value of natural logarithm of absolute value of cosine t over 2, plus, of course, a constant. But I don't need the absolute value because, remember, t is between minus pi and pi, and in this interval, cosine t over 2 is positive. Okay. For the second entry, I guess this is easy. 1 integral of integral of 1 is just t t plus I have another integration constant c2. So my vector v is the vector. For the first entry, I have 2 natural logarithm cosine t over 2 plus c1. And for the second entry, I have t plus c2. And for the solution of the system, I multiply the fundamental matrix with this v. But remember, for our equation for y, we take the first component of x. This means in this matrix multiplication, we multiply the first row of the fundamental matrix, of course, which is the row y1, y2, y1 and y2, with v. So we take our solution y, then in the first row of the fundamental matrix, we have y1 and y2. We take y1, multiply it with the first component of v, which is 2 ln cosine t over 2 plus c1, plus y2, and we multiply it with the second component. And what is y1? Y1 is cosine t over 2. And y2 is sine t over 2. So if you take the constants, you have constant c1 times cosine t over 2 plus the constant c2 times sine t over 2. So this is the piece coming from the homogeneous equation, what we called y sub h. And then if you take the pieces without the constants, we have 2 cosine t over 2, natural logarithm of cosine t over 2, plus t times sine t over 2, and that piece is your particular solution. But you consider both of them at the same time, together with the integrating constant c1, c2, you get both pieces at the same time. So this is the solution. And remember, t is between minus pi and pi. This is given in the question. This interval is given in the problem. We do need this interval because we have in the solution, cosine t over 2, sine t over 2 is fine, but in the solution we have natural logarithm of cosine t over 2. So we need an interval where cosine t over 2 is not 0 and is not 0, it's greater than 0. Natural logarithm, in order to take the natural logarithm, it has to be greater than 0. So this interval is important for the solution to make sense. Okay, now I want to do another example of higher order. The computations is going to be when you have a higher order, you have a larger matrix. You do need the matrix multiplication because, okay, we need all components of this vector v we find. You see, the first component is multiplied by y1, the second component is multiplied by t2. So you need both components, not just the first one. So it means you do need some computations to find your vector v. And when the order of your equation is higher, it means longer computations. I have another example. Again, this is from lecture notes of Özgür Kişisel. I'm going to do the same example. I'm going to share it on Auto class, lecture notes of Özgür Kişisel, so you can look it up there. But it's going to be some long computation. I want to show you all the steps involved. So I'm going to do this in the next video. That's all for now.